Calculus. I've got a new video for you, 4.9. I think we're nearing the end of this mammoth long chapter of exponentials and logs, or perhaps it just feels that way because we had Thanksgiving break separating these things. Anyway, operations with something called the natural log. Now, I'm not going to get too big into the details of where the natural log comes from. There's a mathematician hundreds of years ago named Leonhard Euler, spelled E-U-L-E-R. Strange way to spell Euler if you're not Swiss. I think he was a Swiss mathematician. At any rate, well, Euler came up with this number, E. All right, it's approximately 2.7. I'm not going to throw out there a bunch of history behind what it is, although I would look it up if I were you in a YouTube video. If you get bored over this pandemic, stay at home, remote learning, all that business, look up E and discover what it actually means. But at any rate, what we're talking about with the natural log is log base E is the natural log. And it's abbreviated as ln on your calculator. I think it has something to do with a French phrase with like log something natural. I need to work on my history, right? So, at any rate, what I want to do is show you how the natural log works its way into solving equations, and let's get to it. All right, so despite me giving the clunkiest introduction to a video probably ever, I think we can still salvage some learning opportunities here. So, how do we solve an equation where you're given an exponential function where the base is e? Well, if you want to, just envision that e is approximately some constant number, okay? 2.718-ish. So think about it like this. Would you be able to solve an equation where it was not 3e to the x minus 9 equals 21, but 3 times 2.718 to the x power minus 9 equals 21? So just think of the e as that number. So what would you do to get that variable by itself? Well, you first need to get rid of the 9. I'm going to add it to the other side because it plays nicely with the 21. And then I'm going to divide out that 3. So I've gotten the quantity that is not interrupted by subtraction or multiplication. I've got an exponential base by itself. Now the question is, how do we get rid of exponentials? We apply a log to both sides in which the base of the exponential matches the base of the log. So if I log base e the left-hand side, the two bases neutralize one another and I'm left with x. So what do I do to the right-hand side? I apply a log base e to 10. And we said that log base e was the same as the natural log. On your calculator, it's ln. So the natural log of 10 is going to be your solution. So what is the natural log of 10? Well, make sure you see that ln button right there. You're just going to push that. And then you're going to push 10. It's going to be a decimal. Woohoo! 2.303. And that's your answer. So we solved an equation which had an e exponential. So I don't know, I'm looking back at this and this doesn't seem to be too clarifying for you. Just make sure you get e to the x by itself before you start natural logging anything. So look at number 2. Number 2, we have an exponential base by itself already. So we're good to go. You can log base e the left, which is the same as ln, natural log, and then natural log the right-hand side. These cancel each other out. Remember, this brings itself down. The property of a log says whatever the exponent is to the exponential can be brought down as a coefficient. And then the natural log of e is like log base e of e. They cancel each other out. It's 1. On the right-hand side, you got natural log of 2, which is some decimal. I think it's like 0.69-ish. It's 0.693. All right. So now we've got we've got an equation with an x squared. We got an x. We got a constant. We need to bring everybody to the same side and apply the quadratic formula. So why don't you guys pause the video and see if you can do that on your own. Okay, we're unpaused now. So now we are going to apply the quadratic formula to both sides. It's pretty safe to say that you can't really factor this by conventional means if it's got 0.693. By the way, that's an abbreviation of that. I rounded it. So x equals, you know what? I think we can get rid of everything from number 1 here. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now do some plugins. B is 5. A is 2. And C is negative 0.693. Actually, if you want to, it'll be more exact. You can multiply by the negative natural log of 2. I can put the 0.693 in there if I want to, but hey, that's 1, 2, 3 buttons. That's 1, 2, 3, 4, 5, 6 buttons. I just saved half button pushing experience. But I explained it, so I lost the time that way too. Okay, plug in A on the bottom. Do the calculator magic. Let's see here. And you get 2 solutions out of this. X is approximately 0.132 and negative 2.632. Now, if you want to know what that number inside of the square root is, if you're not getting the right answer, the number inside of the square root should be this, 30.545. Okay, that's it. These solutions should both be protected because the answer to an exponential equation originally generally doesn't have any extraneous solutions because you can plug a negative into an exponent. It yields a proper solution. All right, what else we got? Oh, what happens? Okay, so that's if you're given an exponential equation with e as a base. What happens if the natural log shows up? Well, it's the same idea as when we were doing the solving equations with logs. We're supposed to condense each set of logs to 1 so that we can do the exponential to both sides. So when you look at number 3, this one's a lot more straightforward. All we got to do is get the natural log of 8x by itself first. So I see the 21. It needs to move to the opposite side. Get negative 6. This negative 3, since it's being multiplied by the natural log of 8x, you can divide it out. And that's okay in this case because the opposite side's a constant. Negative 6 divided by negative 3 is 2. Now, there's a couple different moves you can make at this point. What you can do to visualize this better is convert ln into log base e. Yeah, ln is the same as log base e. And the rule before was if you exponentiate the expression in which the base of the log matches the base of the exponential, so I'm going to take it e power here, e power there, then the exponential base and the logarithm will cancel each other out. So whenever you see the natural log, you can apply an e. If we do the proper channels, you know, we got to follow the rules of logs. And that gives you 8x on the left equals e squared on the right. I'm not even going to do the decimal for that because it's easier to type in e squared in my calculator divided by 8 to get that solution. So the solution for number 3 is x equals e squared over 8, which comes out to be approximately, I'm guessing it's going to be somewhere around 1. E squared divided by 8, it's 0.924. All right. Check out number 4 now. You've got a group of logs on the left and you've got a logarithm on the right. We need a clean log on the left, a log without any coefficient, and it's just got to be one of them. Now, if you recall, a log plus a log, when they have the same base, they both have e as a base, the addition turns into multiplication. So it's log base e, or natural log, of 3x plus 1 times x minus 4. Rewatch the 4.7 video if this looks like complete mystery to you. Right, so that converts the left-hand side to a clean single log. On the right-hand side, it is not a clean single log because there's a 2 in front of the natural log right there. So what we need to do is use the property that says exponents can become coefficients, but coefficients can become exponents with logarithms. So that 2 can travel up to here. It's the natural log of x squared. So we got a clean log on the left. We got a clean log on the right. You can exponentiate out those logs. So if I apply e to both sides, I don't necessarily need to do the change where I turn the natural log into log base e. The natural log is the log base e. Cancel, cancel, and you're left with, we got to do some algebra on the left-hand side. 3x times x is 3x squared. 3x times negative 4 is negative 12x. Plus 1x, that's negative 11x. And then minus 4 equals x squared. So now we got one of those pesky quadratics. I'm going to subtract the x squared from both sides and get 2x squared on the left, 0 on the right. Now I got a sneaking suspicion that this is not factorable because what multiplies to give us negative 8 and adds up to give us negative 11? There's no combination that makes that happen. So we do the quadratic. X equals negative b plus or minus b squared. I'm just going to drop the negative because you're squaring it. Minus 4 times a times c. Don't drop the negative on that one. And then times 2a, which is 4. All right, so this will be 121 plus 32. So that should be 143. Let's double check my math on that. Squared minus 4 times 2 times 153, my bad. So x is going to be approximately, if we do both the plus and the minus, you get 5.842 and negative 0.342. Now be very careful, because we're back in logarithmic land, where the original equation was a logarithm, which means, okay, you still have this domain restriction. Even the natural log behaves like a log. It crosses the x-axis at 1, just like the other ones do. Looks like that. So if you get a negative number, it doesn't yield any corresponding part to that log function. So let's check negative 0.342. It violates that there and this one here. So this would be an extraneous solution created with this Frankenstein step where we put two individual parts together. But the 5 is okay. You plug in 5.8 here, it's a positive. Here, it's a positive. Here, it's a positive. That's a positive. All right, how much time? 16 minutes and 30 seconds. I think we need a break. Let me just check the next example. Yeah, you know what? Let's take a quick break.